Everyone can see?
Correct.
Should we begin?
Correct.
Are we ready? Okay, so I want you to write down what is a and what is a we should all be able to answer these two things. Is this what everybody got? Now I want you to write examples. But the most obvious one that everybody should get are those two. Yeah? Did everybody get sort of the same thing? Excellent. So we're all on the same page, right? Speed is what your speedometer measures. Velocity is what your GPS measures. Because your speedometer does not care whether you're going north, south, east, or west, correct? But your GPS does. Very simple to remember, right? So those are basically it. However, today we will do a little bit of revision on vectors. So scalars are easy, right? So if I was to ask you the definition of speed, what would it be? If I was to ask you the definition of velocity, what would it be? Excellent. Which means I have to do what to it? The same formula, but what's the difference? That on top of it, right? That little line takes your quantity, whatever you have, from a scalar to a vector. Agreed? How do we actually write this? What's the difference between delta and D? Delta is big, D is tiny, right? So how do we go from this delta to this delta? D, it's in the limit when delta T approaches 0. Got it? So delta, whatever it may be, goes to D in this limit. Everybody's seen this written before, right? And that's an L, right? So if you wanted to write speed.
Wait, does that say with the delta T point to 0, right?
Yep, hold on, I'll write it out. That means in the limit of when delta T approaches 0, speed becomes dx over dt. Got it? All you're doing is you're taking the big speed, the average speed, and you're squishing it down to a smaller and smaller interval. Okay? Same thing with velocity. When velocity is small, we call it instantaneous velocity and instantaneous speed. Sorry, remember those words from intro 1? Instantaneous velocity and instantaneous speed. So velocity instantaneous velocity will be in the limit, that's an L, when delta T approaches 0, delta X over delta T. Oh, wait, I messed up. Hold on. This should be the big T, big D and big dx. So this should be delta X over delta T approaches. This is written as dx over dt. So that was me messing up, okay? So if you ever see dx over dt written, that means it's in the limit when time is very, very small. Make sense? Same thing here. This will be in the limit when the vector d. Okay, so now everybody got this, right? Yeah. We're clear on on the way we're going to say things. By the way, if this is velocity, how will we define acceleration in this class? Just by the way. Yes, so the way we define acceleration in this class, which is dv over dt, or instantaneous acceleration will be dv over dt, where delta t goes to 0, is dv over dt. And since we are now in Newtonian classical mechanics, instead of writing dv, we will write d squared x over dt squared. Small change is what is going to convert our physics 1 into Newtonian classical mechanics. This is what makes it a second order differential equation. So remember when we were talking about, oh, by the way, before we go on, sigma f is what? MA. We usually write m d delta v over delta t. However, in this class, sigma f will be written as m d squared x over dt squared, which in fact will take our force, that is Newton's second, everybody remembers Newton's second law, right? That will take our Newton's second law and make it into a second order differential equation. Excellent. Okay, I'm gonna erase this because that was just, oh, by the way. Wait, anybody still writing?
Yes.
Okay, hold on. I was just gonna erase it. We'll talk more about this later. Okay, everybody got done writing this? So now we're gonna start talking about vectors. Can you guys write a vector with its components on your papers? Any vectors. I want you to write a vector A with its 3 components, X, Y, and Z. How would you do it? I'm not going to come and look at it. I just want to see, I want you guys to just write one. X, Y, and Z. And the total vector should be A. Does your vector look like this?
Although I put numbers for the A.
So again, remember this is Newtonian classical mechanics, very little numbers. Okay, only when I tell you numbers are we going to put numbers. Use variables. What are IJK? So what do they tell you? What directions?
A, X, Y, Z.
Good. What does I unit vector represent? What does J unit vector represent? And what does K unit vector represent? Okay, excellent. This can also be written as AX, AY, AZ with curly brackets. Now, on your 3D coordinate systems, I want you to tell me where 1, 2, and 0 will be. Talk to each other. Do you guys all agree? Talk to somebody. Yeah, make sure we're all okay. Good. Now draw. Where would 2, 3, 4 be? Do we all have it? Now I want you to do one more thing. Draw 3, 4, 2. Keeping in mind where the other one was. Are we talking to each other? Yeah? Are we all agreeing?
Yeah.
Good. This is how vectors work. Got it? So every single time you see a picture that is drawn like this on paper, and they tell you this is happening, it's actually coming out of the paper towards you. Got it? There is no way for us to draw on a 2-dimensional plane that picture. So what we do is we try our best and we come up with this. In general, I tend to think X, Y, Z. In most cases, because in my head, Z comes up. But it could also be whatever you want. But remember, we're living in a right-handed coordinate system, right? So that's always going to be X, Y, Z. X, Y, Z. No matter how you flip it, it's going to be X, Y, Z. Good? Are we clear about vectors?
Oh, we're clear.
Okay, excellent.